So if you wanted to factor 9y squared minus 15y to the third, what would you do? Where would you start? What are your thoughts? Say again? 3. Okay, so 3, the number 3 plays an important role in factoring this expression. Where is that 3 coming from? What's going on in your head there?
3 times 3 is 9, and 3 times 5 is 15.
Okay, so the first thing that is focusing on here are the coefficients, the numbers, the numerical factors in these expressions. And he's factoring each one of them out. The first thing you do in this module is get a quick refresher on how to factor whole numbers. You can factor 9 into the product of 3, and we can factor 15 into the product of 3 and 5. And what role does 3 play in these factorizations? Or what do we call the number 3 with respect to the numbers 9 and 15? Right. Yeah, in fact, it's 2 things, right? It's a common factor because both of those numbers have 3 as a factor, but it's also the largest such number, which is a factor of both 9 and 15. This is the greatest common factor. Finding common factors is the top priority when you factor an expression. Finding the greatest common factor just means you're going to factor with the fewest number of steps possible, right? You're taking the most efficient route at factoring the expression. So the first thing we'll do is demand that 3, the greatest common factor of the numerical coefficients, be something that we factor out in this problem. And I'm just going to write an empty set of parentheses next to it. So going along with the theme of factoring being the opposite of foiling, we need to then figure out, if we were to go backwards, if we were to redistribute and multiply, we should get back to the original expression that we started with, 9y squared minus 15y to the third. So with that in mind, what coefficient does the first of the terms inside these parentheses need to have in order that when we go backwards, it becomes 9y squared? It needs to be a 3. By the way, here's another way that I like to see that step that we just did, because sometimes it feels like an art form, but it need not feel like an art form. Sometimes, and this is another one of those classic suggestions of mine that you can take it or you can leave it, depending on if it clicks with you or not. Once we've identified that we want to factor out a 3, I like to see it as follows. I like to see it as 2 things that we're doing. I can see it as multiplying this expression by 3, right? Sort of just take a 3 and multiply the whole thing that we started with by 3. But we can't just get away with doing that, because we're going to triple the value of this expression. So at the same time that we divide everything, the same time that we multiply everything by 3, we also need to divide everything by 3 so that we're not changing the value of this expression overall, right? I can't just triple everything and get away with it. If I triple everything, I also have to divide everything by 3 to wash, so that everything comes out in the wash. And why I like this is that now this gives me a recipe for how to find that coefficient that gets left behind. It's just the result of this 9 and this 3 reducing to give us 3 over 1. And with that in mind, what becomes the coefficient in the second term after we factor?
I got a question.
Yeah. The greatest common factor, in a way, is the rock upon which you build your church of factoring, right? It's the thing you start with in the very beginning. If you find the greatest common factor, that's going to get you a lot of juice toward factoring this expression. So start with it, write it out in front, write an equal sign, and then write your GCF right away. And then leave a little bit of space, because we might not yet have the entire GCF, and then put your empty set of parentheses.
Technically do something like this. So you pull the 3 out.
So bringing that 3 as the greatest common factor out to the front in the beginning then lets us focus on the numerical coefficients for a little while, right? That when we pull the 3 out of the first term, we end up with a new coefficient of 9 divided by 3, 3. When we pull a 3 out of the second term, we end up with 15 divided by 3, or 5, as the coefficient that belongs there. And so now we've handled everything as far as we can go with just numbers. Now we've got to tackle the variables. So what happens next, now that we've handled all of the coefficients? How are we going to deal with the fact that we had a y squared and a y to the third?
Subtract them.
Okay, well, what does subtract them look like?
You take 2 away, so that's basically nothing, and then you are left with y first.
Okay. All right, I like the way you're thinking. So what we want to do is we want to take away from these two terms as many powers of y as we can, right? If I take a maximal number of powers of y away from this first term, the 9y squared, that's going to leave me with no y's at all left in that term. If I then take the same number of y's away from the second term, I'm going to have a y left over. So that's your mental frame that you've got on top of this, and it will work. What I'd like to do with that observation is take it another step and kind of think about it from the perspective of greatest common factor again. So we found the greatest common factor of 9y squared and 15y to the third. We found the greatest common factor of 9 and 15, and we said that it was 3. But why don't we include the variables in the process of factoring as well? After all, 9y squared is nothing more than 9 times y squared. 9 is 3 times 3. Y squared is y times y. So include the variables, kind of treat them like they're numbers when you factor these. It's a good way to kind of understand what we're doing, where it comes from, if you like. 15y to the third, the 15 is 3 times 5. And then y to the third is, let's just break it apart in one step into y times y times y. And now, looking at these two factor trees that we just drew, we maybe, hopefully, get a different perspective on the greatest common factor. We can still see the greatest common factor of the two numbers. Right? It's that 3 that's sitting right there. But what else do these two terms have in common? They have a y in common, namely, so here's a y that they both share. What else do they have in common? Another y, exactly. But once we've exhausted those, now there's nothing else that's left that they have in common, right? The first term has another 3 that the second term doesn't, and the second term has a 5 and another y that the first term doesn't. So at that point, we're done. Which gives us the perspective that the greatest common factor of these two terms is not just 3, but in fact, what is it? It's 3 times y times y. Yeah, or if you like, 3y squared. So when the question is, what is the greatest common factor of these two monomials? That includes not just the greatest common factor of the coefficients, that would be the number 3, but it also includes the greatest common factor of the variable powers that reside inside of those expressions, and so it also includes a y squared. So the 3 tells us that we can maximally take away a 3 by dividing from both the coefficient of the first term and the coefficient of the second term, which is what we've already done. But the y squared now tells us what John was observing before, which is that we can also take away 2 powers of y from the first term and from the second term. And if I do that using the same procedural suggestion that I made up here, which is to say multiply by it, but then also divide by it, now we can kind of see what's left over for the terms inside the parentheses. When I divide 9y squared by 3y squared, we know that the 9 and the 3 get together to give me a 3 in the quotient. What happens to these powers of y? They cancel. They go away. They leave us with 0 powers of y, which is to say they leave us with no y's at all.
Because when we divide, we subtract.
When you divide, you subtract the exponents, exactly, which is why I say 0 powers of y there. It's 2 minus 2. So if we wanted to be really glib, we would say y to the 0 here in that term. But y to the 0 is nothing more than the number 1. So we don't have to write it at all when it comes to multiplication. And the quicker way to say it is just the way that Joe originally said it, just they cancel. Y squared on top, y squared on bottom, those are common factors which cancel in a fraction. So the first term in the cofactor here, in the parentheses, really is just 3. What about the second term? In 15y to the third divided by 3y squared. We know what happens to the 15 and the 3. What happens with the y's? Yeah.
You subtract them, so you're just left with 1y?
Yeah. You subtract the exponents, 3 minus 2, leaves me with 1 power of y that survives into that term in the final factor. And again, whenever you have a single power of something, you don't have to write the exponent if you don't feel like it. And the last thing to do is just to fill in that subtraction sign. that subtracts these two terms. Because we didn't factor out a negative number, we don't change the sign that we got in the middle here. So what was started the problem as being subtraction ends the problem as being subtraction as well. So as I say, this is kind of the cornerstone of your factoring techniques. It's the thing to think about first. When you're given an expression that just says, factor this, first thing to think about is there a greatest common factor that I can do this with? Because if there is, this is what you want to go to first. In some problems, there may be more to do after this, but the more stuff that you would do after this, you would do to the simpler version of what's now inside these parentheses. If there were more factoring, we would do it there. In this example, there isn't.